All right, in the second part of 4.2, we're going to start with graphing logarithmic functions. So we already mentioned in the first part that exponentials and logs are inverses of each other, right? And in 4.1, we actually talked about graphing exponentials. So let's start by reviewing that real quick. Let's graph 2 to the x. Okay, and we actually already did this in the first lesson, so I'm not going to spend too much time talking about this. But let's say I were to plug all of these values in. Well, 2 to the negative third would mean 1 over 2 to the third, so that would be 1/8. 1 over 2 squared would be 1/4. 1 over 2 to the first is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4, and 2 to the third is 8, right? So if we plot those, -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8, we get our function that looks like this. Okay, so since logs and exponentials are inverses of each other, okay, remember one of the big ideas that we talked about when we talked about inverses was that all of the x and y values would be switched. These are inverses of each other because they have the same base, right? 2 to the x and log base 2 of x. So to graph this function, all I'm going to do is flip these x and y values. Since these functions are inverses, I can say that these points will all be on the graph of log base 2 of x. So if I were to plot these, let's see, 1/8, -3, 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, and 8, 3, we get a graph that looks like, oops, that looks like this. Now, also remember that when we talked about exponentials, or I'm sorry, when we talked about inverses before, they are reflections of each other across the line y equals x. And hopefully we can see that if we put that line y equals x in here, these are perfect mirror images of each other. That is true of any exponential in its corresponding logarithm. Okay, so let's talk a little bit about the shape of this graph, right? We talked about what an exponential curve looks like. If it is not shifted, it has a horizontal asymptote of y equals 0. A logarithmic function, if it's not shifted, would have a vertical asymptote of x equals 0. Right? It would still increase without bound, but it keeps getting smaller. The increase keeps getting smaller and smaller. An exponential, the increase keeps getting larger and larger. All right, so let's try one more example of that. Let's do 1/3 to the x. And we talked about an example similar to this before, where, let me, I guess, stay consistent here. We'll do this one in purple. So whenever we're plugging in negative values, let's just do a few here. So 1/3 to the negative second, I would need to bring that 3 to the negative second to the numerator. And that would be 9 here. Bring that 3 to the negative first to the numerator. That would become 3. Anything to the 0 power is 1. 1/3 to the first is 1/3. And 1/3 squared would be 1/9. So here we talked about this idea that these would be decreasing functions whenever the base of the exponential is in between 0 and 1. So this will end up looking something like this. So then for the corresponding log, right, if it has the same base and it is the inverse, all I'm doing is switching the x and the y values. Right? So 9, -2, 3, -1, 1, 0, 1/3, 1, 1/9, 2. So this would look something like this. 3, -1, 0, 1/3, 1. Right, so we get something that looks like this for that log. And we can see that these are actually reflections of each other across the line y equals x. Okay, so let's just jot down some basic properties of exponentials and logs in terms of the graph. Right, so we said that the domain of an exponential is all real numbers, right? Negative infinity to positive infinity, but the range was just 0 to infinity. And again, that's before we perform any shifts. If we look at our pictures then, what that means for a log, the domain is just going to be 0 to infinity, but the range will be all real numbers. And that's true of any inverses. I would literally just switch the domain and the range if two functions are inverses of each other. Now, for an exponential, the x-intercept, and again, this is before we do any shifts, the x-intercept is the point 0, 1. Oops. The y-intercept then, well, if I look at my graphs here, the y-intercept of an exponential, whoops, I did that backwards, didn't I? Apologize for that. The y-intercept is 1. The x-intercept, if I look at my graph, there is no x-intercept, right? Because the exponential function does not cross the x-axis. Then it's just going to be the opposite for a log, right? If we go back to our graph, the x-intercept of a log is at 1, but there is no y-intercept because the y-axis with the line x equals 0 is a vertical asymptote. So x-intercept of 1, no y-intercept. And then we've already mentioned that, again, before any shifts, the asymptote of an exponential is the x-axis, which would be the line y equals 0, and the asymptote for a log is the y-axis, which would be the line x equals 0. Okay, so now let's talk about shifting logarithmic functions a little bit, right? So just like we mentioned with shifting exponentials, right, we talked about shifts a lot in a couple of chapters ago. So here, if we have an a value, a number out in front of the log, that is a vertical stretch or compression. A b value is a horizontal stretch or compression. C would be a shift left or right, and D is a shift up or down. So let's try an example where we graph log base 2 of x, which we already did that, right? We did that in the first example. So let's just sketch that on here again. Right? And we said that we would get points here, 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 here. Right? So here's what that graph would look like. So now we need to remember our rules of all these shifts. This is a shift to the right one. Right? Remember, since this is a negative sign already on the inside, okay, I'm going to go to the right one. We're essentially taking the opposite sign of this to think about the direction left to right. Then this would be a shift up 3. So I'm just going to take each of these coordinate points and go right 1, up 3, right 1, up 3, right 1, up 3, right 1, up 3, right? So for each of these, we can see what is happening, right? So my new graph is going to have a vertical asymptote shifted to the right one. If my old vertical asymptote was at the line x equals 0, my new vertical asymptote is going to be at the line x equals 1. Right, so let's connect these dots here and get my new graph. All right, then the domain and range, well, if the old domain was 0 to infinity and we shifted to the right one, my new domain is going to be 1 to infinity. The range then is not going to change. The range is still going to be negative infinity to positive infinity because the range is all of the y values that we reach. Okay? So on the back then, we have a few applications. The first is continuously compounded interest. And we talked about this already. Our formula for continuously compounded interest, remember, was the amount equals the principal times e raised to the rate times time power. So now in each of these examples, we're going to end up needing to use a log to solve for the missing piece that we want. So here, this says we invest $4,000. So $4,000 is my starting amount. That's my principal. Continuously, so that tells me I'm going to use this formula. Whenever we see continuously, right, we're using PERT. And 11% is the rate. So 11% as a decimal would be 0.11. We want to figure out how long it takes. So the time is what I don't know. That's what I'm going to be solving for. And I want my final amount to be 53,000. So let's plug all of this information into my A equals PE to the RT formula. So I'm going to have 53,000 equals 4,000 times E to the 0.11 T power. So I want to solve this equation for T. The first thing I want to do is get the exponential portion by itself. So that means I'm going to divide both sides by 4,000. Now, I'm not even going to bother putting that in the calculator yet. I'm just going to write it just like that. Okay? Now, we talked about this in the last section. Whenever I have a variable in the exponent, what I want to do is rewrite this as a log. When I do that, right, I'm going to say log base E. Now, log base E is a natural log. So natural log of this, of my 53,000 over 4,000, is going to equal the exponent. Okay, so we talked about rewriting like that. Another way to think about this is just taking the log base e of both sides of the equation. If I take the log base e of both sides, or the natural log, we said, well, if we have the same base of the log and the exponential, they essentially cancel each other out, and then we're just left with the exponent. So then the last thing to get t by itself would be to divide both sides by 0.11. And now this I can put into the calculator. Right? So I can say natural log of 53,000 divided by 4,000, close the parenthesis, and divided by 0.11. Okay, so that tells me it's going to take 174.292 years. Okay, so my answer is 174.292. All right, let's take a look at another example. This one's very similar, but it just says how long would it take your money to double if you invested P dollars at a rate of 3.7% compounded continuously. So again, that tells me I'm going to use A equals PE to the RT formula. So let's take a look at what we know. Well, I mean, the only number I see here is the rate. So the rate is 3.7%. As a decimal, that would be 0.037. But now it says I want to double my money. So whatever I start with, I want to end with twice that. So we can say that no matter what the principal is, I want to have twice that at the end. That's really all the information that we have. So let's plug it in and see what happens. So if I put 2p in for a, I want that to equal the principal times e raised to the 0.037 t power. Well, now if I divide both sides by p, the p's will cancel out on both sides. And I'll just be left with 2 equals e to the 0.037 t power. Now we are to a point where I can rewrite this as a log. Or again, we can think about it as taking the natural log of both sides. So when I do that, I'll have the natural log of 2 equals 0.037t. Right? We can think about the lazy 7, right? The base of the exponential would become the base of the log. So log base e of 2 equals 0.037t. Or we're thinking about taking the log of both sides. So now, again, the only thing I need to do is divide both sides by 0.037, and we can put that into the calculator. So natural log of 2 divided by 0.037, and I get 18.734. So in this case, a little bit more realistic time frame, 18.734 years. All right. In the final example, we want to solve for the rate. Right? So similar process though. I want my, well, first, compounded continuously, so we know we're using this formula. Then my starting amount, my principal, is 10,000. I want my final amount to be 80,000. And I want my time frame to be 20 years. So I'm solving for the rate this time. Same process though. So 80,000 equals 10,000 times e to the r times 20 power. Right? So divide both sides by 10,000. 80,000 divided by 10,000 is just going to be 8. Now I can rewrite this as a log. So natural log of 8 equals 20r. Divide both sides by 20. We'll just have the natural log of 8 divided by 20, and that we can put into the calculator. Natural log of 8 divided by 20 gets me 0.10. Let's go out. So since this is going to be a percentage, we're going to end up moving the decimal a couple of spots, right, if we want to write it as a percentage. So to take this percentage out to 3 places, we would actually go out to here, right? So 0.10397 is the rate. And then if we wanted, we could rewrite that as 10.397%. Okay. In our final application example, we're going to take a look at Newton's law of cooling. This is actually a really cool application. This is a model for whenever you take something that's either hotter or colder than room temperature and place it in the room. This is a model for the temperature that that object attains. For example, if you take something out of the oven, this formula models the temperature of that thing over time. Or if you take a cold drink out of the fridge, this would model how much it warms over time. So this formula, I will never expect you to memorize this. If we have a problem dealing with this on a test, I will give you this formula. You just have to understand how to use it. Okay, so let's take a look at what each of these pieces are. The left side here is just the temperature of the object, right, at whatever time we're talking about. The T sub S is the surrounding temperature, or in other words, the room temperature of the object. T sub 0 is the initial temperature that we start with, right? So if you take something out of the oven and it's 150 degrees, right, that's the initial temperature. And then the K value is a constant that depends on the object. So for all these problems that deal with Newton's law of cooling, the first thing you have to do is solve for the K value. To do that, you're generally given a reference point. For example, well, let's just look at this first example. Okay, so Marianne's has discovered that when coffee is poured from a coffee maker whose contents are 180, so we're starting at 180. That's my T sub 0. That's my initial temperature. We're pouring this coffee into a non-insulated pot. After 1 minute, the coffee cools to 165 degrees. Right? So this is our reference point that we're going to use to solve for K. After 1 minute, so when T equals 1, the temperature of the object is 165. Then we're told that the room temperature is 72 degrees for this scenario. So to answer both parts A and B here, the first thing we have to do is figure out the K value. So to set up my equation here, I'm going to say the temperature of the object right now is 165. The starting temperature, or I'm sorry, the surrounding temperature was 72, plus my starting temperature, my initial temperature was 180, minus the room temperature again, times e to the negative k. And this instant, the instant that the coffee is 165 degrees, my t value is 1, right? Because it's after 1 minute. So temperature at the current time, room temperature, initial temperature, and then the time that has passed. So we now want to solve this for k. So I'll subtract the 72 over. That would be 93 equals, then 180 minus 72 is 108. So I'll have 108 times e to the negative k. Then I want to divide both sides by 108. And now that I have my exponential by itself, I can rewrite this as a log. So this would become natural log of 93 over 108 equals negative k. Then to get k by itself, I would just need to multiply both sides by -1. So we end up getting negative natural log of 93 over 108 equals k. So we can put that into our calculator. So negative natural log of 93 over 108. All right, so I'll write this down, but I'm going to store this as well. To store a value in your calculator, we would press this STOA, and then I'm just going to store it under alpha A so that my calculator remembers that, and then I just have to type in alpha A whenever I want that value. Right? It might also make sense to just store it under K. Right? What was that? 0.1495. All right. So now we can take this value into our formula, right? So let's back up and say the temperature at time t equals the surrounding temperature plus my initial temperature minus surrounding temperature times e to the negative kt. So now I'm solving for t of 10. I can do that now that I know my k value. So t of 10, after 10 minutes, I'm going to say t of s, the surrounding temperature, plus my starting temperature minus my initial temperature times e to the negative 0.1495 times 10. Right? Once I solve for k, I'm just plugging all of this information into the formula. So we can evaluate that now. 72 plus 180 minus 72 times e to the, and since I stored that value under a, I can just put alpha a times 10 up here. Oops, I forgot my negative sign, didn't I? Insert my negative sign there. There we go. So 72 plus 180 minus 72 times e to the negative k times 10 power. So the temperature of the coffee after 10 minutes is going to be 96.211 degrees. Oops. Okay. Now in our second question, we want to solve for a time. We want to know how long the employees should wait before pouring the coffee if it is to be delivered at 120. So I want my temperature to be 120. Right? So I'm going to say, I'm going to write it all out. So I want this to be 120. And then the rest of this information is the same. The surrounding temperature or the room temperature was 72. My T sub 0, my initial temperature was 180 minus T sub s times E, and we already solved for K. This is the same scenario, so K is going to stay the same, 0.1495. But now I'm solving this for T. So I would subtract the 72 over 120 minus 72 would be 48 equals 108 times e to the negative 0.1495 t power. Divide the 108 over. And now, once I have the exponential by itself, we can rewrite this as a log. So log base e would be a natural log of 48 over 108 equals negative 0.1495 t. And then just divide both sides by the negative k value. And I can put this whole thing into the calculator. So natural log of 48 divided by, what was it? 48 divided by 108 divided by my negative k value, right, which we stored in the calculator as a. So I can just say divided by a negative a. And that tells me that the coffee will be 120 degrees after 5.423 minutes. Okay, so Newton's law of cooling is actually a really interesting application here. All right, so that is it for this video. The final question is going to pop up asking you what questions you have.